If we look at a piece of a nerve fibre, we see that the cell produces large negatively charged ions called A-, meaning large anions, which are trapped inside the cell and can't get out. It also actively excludes sodium ions, the Na+. And that leads the inside of the cell to be strongly negative. To some extent, this is compensated by passive migration of chloride ions, negative, out, Cl, and potassium ions, K+, inwards, which are then not in equal concentrations inside and out. When part of the cell fibre becomes active, however, what happens is that there is a leakage of sodium. Sodium is allowed to leak into the cell, thus carrying positive charge inside and making the inside go positive. As soon as that happens, about a thousandth of a second later, the cell becomes leaky to potassium, and potassium moves out, taking positive charge outside the cell again and restoring the status quo. If we have an active region in the middle, which becomes positive, then electric currents are set up from the active region to the surrounding regions. The currents go from positive to negative, and they cause the resting region to become leaky to sodium, so that region in turn becomes active, and the action potential moves down the membrane. And it can move at quite a high speed. At the end of the fibre, there is a slightly swollen terminal which contains a number of little capsules called vesicles. And inside those are chemicals that are made by the cell. The action potential comes along to the end there, and it causes a few of those vesicles to come to the outside of the cell, burst and release their contents, and they diffuse across to the next cell, which is just a short distance away across the gap. In some nerve terminals, those chemicals cause a leakage of sodium, so that they tend to excite activity in the following cell. In other terminals, different chemicals cause the leakage of potassium, which makes the next cell become less active. Now, in the brain, that next cell may have 10,000 terminals coming onto it, some exciting it, some inhibiting it. And, well, its own action is determined by the sum total of all that happens, all these 10,000 inputs. So it's rather like a computer that is receiving a whole lot of information through different channels and having its own activity coordinated. When it fires its own action potential, that may go out through branches of the fibre to as many as several thousand other cells. And this is a real piece of tissue. It shows a motor fibre branching to terminate on muscle fibres, and each receives a terminal from the motor fibre, and that whole collection forms a motor unit. When we make a muscle contract, an action potential goes down and each one makes a number of muscle fibres contract, and the whole muscle is controlled in that sort of a way. Well, I'd like to show you now an actual action potential. We're going to show it in earthworms. Earthworms have, in common with other invertebrate animals, their nervous systems just inside the skin on the ventral or underneath side. Here are some worms living in a wormarium. There's one on top here. And you know that if you poke a worm, it will contract quickly along its length. Let's see if this one will do it now. I pulled in its tail quickly. This is part of an escape reaction. If a worm is unwise enough to put its head out of its burrow on the lawn during the day, and a bird comes along and pecks at it, it'll pull back into its burrow very, very quickly. It's important to do it quickly. But a worm can't afford to run its nervous system at high speed, because the speed at which an action potential goes depends, for electrical reasons, on the size of the fibre. Big fibres conduct faster than small ones. So for its escape reaction, the earthworm has a couple of giant fibres that run along the body and tell it to contract to get back into its burrow as quickly as possible. We have a demonstration here. I'm going to be helped by David, a graduate student from Queen Mary College. Hi, David. What we've done here is to hang an earthworm over some wire electrodes from which we can record the action potential of its giant fibre system and stimulate action potentials by passing a small shock through the body of the worm at the other pair of electrodes. It would, of course, be terrible for this experiment if the earthworm were to wriggle, so this one has been sedated by being dropped for a few minutes into 10% alcohol, roughly equivalent to the strength of table wine. This doesn't seem to do them any harm at all. They recover afterwards and they don't even seem to get a hangover. So I will now give it a switch on the stimulator. And what we see here on the screen is a spike representing the initial shock that goes down the length of the worm at the speed of light. If I go to the next scale, I can turn it up a lot more, and I get a slower potential there from a second, smaller, and therefore slower fibre system. Let's just measure the time interval. Can we record that, please, David, on the screen? The speed of this now then is about 9 milliseconds, and the distance travelled is near enough 9 centimetres. So the speed then of the action potential in that faster giant fibre is just about 10 metres per second. Well, I said that this giant fibre is used for escape reactions. One of the most spectacular of giant fibre systems is that contained in marine fan worms. It's a different group of worms that live on the bottom of the sea on a muddy environment and construct for themselves tubes of mud in which they live, and you see some here in the tank. They push their front ends out of the tube as a big fan that collects food by filtering the seawater and collecting microorganisms. But of course that's a very tempting morsel for any fish that's going by, and they're very vulnerable. The only escape they can make is to whip back into their tubes at high speed. Now, I'm not going too close to the tank because as I walk up, they often react just to my footfalls on the floor. I creep up on them now. See these very beautiful crowns of tentacles here, but if I tap the tank, they all shoot in. They nearly all shoot in. And that is brought about by a single giant fibre that runs down the body of the worm and is truly enormous. Fan worms have some of the largest fibres known. A section through a fan worm. At the bottom there, just above the skin, is the nervous system containing lots of small nerve cells. And above that, the pale area arrowed there is the single giant fibre, which is much bigger than the whole of the nerve cord, of the rest of the nerve cord. It's up to 1.8 millimetres in diameter, which is huge. It was so big that for a long time people thought that this was a strengthening skeletal element and didn't recognize it as a single nerve fibre. Nevertheless, that fibre can only conduct at 15 to 20 metres per second.